All right, let's look at this part C. This time you're given an ordinary generating function for sequence a sub n, and you're supposed to find the closed formula for a sub n. So this is where you start by just looking at our small collection of handy Maclaurin sequences or series, power series. And I found 1 over 1 minus x quantity squared in my list, and it's n times x to the n minus 1. It comes from the taking the derivative of 1 over 1 minus x. Constant multiplier like 5, or any actually multiplier like it would work with 5x or anything like that too, can be pulled out, left there, and then the rest of the function is a polynomial already. So you don't replace polynomials with Maclaurin series, they are their own Maclaurin series. So I just write the plus 3 plus 7x squared. Oh, that 7 didn't scan very well. That's supposed to be 7x squared there. You can see it in the next couple of lines. All right, so I don't touch that polynomial portion, the plus 3 plus 7x squared, but I need to adjust the Maclaurin series portion of it so that it has x to the n, and I do that by reindexing. First I replaced every copy with, actually first, in this case, what I did first was realize that the 0 term was 0. When you plug in n equals 0, you get 0. So that means you can, for free, start it at n equals 1. Not adding on that first 0 doesn't make any difference. So I put n equals 1, and then I reindexed. I replaced every single one of the n's in that summation with n plus 1. That allowed the n plus 1 minus 1 on the x to become just x to the n. Then there's an n plus 1 out front, and then I have n plus 1 equals 1 underneath the sum, but subtracting 1 from both sides, I get back to n equals 0. So that lets me see the right form. It has n equals 0 to infinity, it has x to the n. It may start at a different index n under that sum. The important thing is that you have to include in your final answer every n that's used in the sum. So that means I'll be using n plus 1, the multiplier on x to the n, for all n's larger than or equal to 0. Oh, and the 5 also, 5 times n plus 1. All right, so let's see. I put one answer on the left, which is fine to leave it as, and then a simplified answer on the right. So on the left, for n equals 0, I need the 5 times n plus 1 from the summation because that includes n equals 0. But then I noticed that there's also an x to the 0 term, that plus 3. So I get 5 times n plus 1 plus 3 when n is equal to 0. Notice this is an ordinary generating function, so I won't have to worry about putting back in a factorial. In an ordinary generating function, the multiplier of the x to the n is a sub n. So that comes into play now for n equals 2. For n equals 2, I will need to use the coefficient from the sum, 5 times n plus 1, because n equals 2 is included in that sum. But then I'll also use the coefficient from x squared added on at the end, the 7. Finally, for all other n not equal to 0 or 2, I just need 5 times n plus 1, the coefficient from the infinite sum. So that's how I got a sub n there. And then if you'd like to simplify it, you can. I usually simplify it myself, basically just so that I can match it up with anybody's answer that came out a little different. It might have a slightly different formula, but with the same simplification, so it's still right. But you don't have to. I can do that part. It's also sometimes nice to simplify it if you want to check your work somehow, which I'll mention how to do that in a second. So that first one, plugging in n equals 0, I get 8. For the second one, plugging in n equals 2, I get 22. And for the third one, that's for any n, so just have to leave it. Now, yeah, for interesting to check your work, for n equals 0, I know that for an ordinary generating function, that should be the value I get when I plug 0 into the function, the original function. And also you would then need to worry about the factorial, because when you plug in, when you're using the ordinary generating function, using the actual function and its derivatives, then you need to worry about the factorial. But plug in n equals 0, then times 0 factorial will just be times 1. So we have 5 over 1 minus 0 squared plus 3 plus 7 times 0. Yep, get 8. So quick double check. To use that second number as a double check, the 22, I'd have to take the second derivative of f, which would use some space. Not terrible if you need to do it. Of course, you use the computer to double check these too. In fact, for these kind of problems, I'll probably make them fairly a small part of the test, since the computer does them so well.